Notes 3.5. It's about mathematical modeling. And we're going to talk about, in particular, um, models for direct, inverse, and joint variation. And then we're going to solve a few application problems. So, just as way of review, in section 2.1, we solved application problems using linear models. And today we're going to use models that involve polynomial and rational functions. That's why this lesson falls in chapter 3. The general linear model is y equals mx plus b. We've worked with that in chapter 2. And for this model, the slope is m and the y-intercept is the order paired 0, b. A simpler linear model is called direct variation. So this model of direct variation is given by the equation y equals kx, where k is called the constant of variation or constant of proportionality. K cannot be equal to 0, otherwise we don't have direct variation. And the graph of direct variation, which is given by y equals kx, is a line with slope k and y-intercept 0, 0, right? Our b term is 0 in this equation. So graphs of direct variation always pass through the origin. You need to be familiar with three interchangeable terms. The first is y varies directly as x, y is directly proportional to x, or you can be given the equation y equals kx. All three of these tell you that you have direct variation when you're doing application problems. Let's try a couple application problems now. So the first problem is very typical. We're going to be given a statement that tells us that we do in fact have direct variation. So the statement that tells us this is the variables x and y vary directly. That tells us as soon as we see that, we can go ahead and write down that the model that we're using is that of direct variation, which is y equals kx. Then we'll be given some other information, and let's see what we're given here. So we're asked to write the model that relates x and y. So that's the first thing. And then we're asked to use the model. So this part here is use the model. Okay, but first we have to write the model. And in order to write the model, we're going to use this given information that x equals negative 18 and y equals 4. So we're going to use that to figure out what k is. So use to find k, which is our constant of variation. So in this case, we're told that x equals negative 18 when y is 4. So we have 4 is equal to k times negative 18. So k, divide both sides by negative 18, is negative 4 over 18, which will simplify to negative 2/9 is k. So if we go ahead and we're going to write our model now, we need to substitute this back in. So we have y equals negative 2/9 x. That's our model. That's the first part of the problem. And then we're asked to use the model. So we're going to use the model. So we're going to find y when x equals 4. So when x equals 4, we're going to substitute in here. So y is equal to negative 2/9 times 4. So that gives us y is equal to negative 8/9. And that's when x is equal to 4. And then the other thing that we're supposed to do is find x when y equals 9. Okay, so when y equals 9, we're asked to find x. So we'll substitute in for y into our model. So 9 is equal to negative 2/9 times x. We'll multiply both sides of the equation by negative 9/2, and we'll get x is equal to negative 81 over 2. And that's the end of that problem. Let's go ahead and try the next example. According to Hooke's law, the example says, the force that is needed to stretch a spring varies directly. So this is the key that tells us that we have direct variation. with the amount the spring is stretched. Okay, so we know that we're going to have our model is going to be F is equal to K, our constant of proportionality or constant of variation, and D, where D is the amount the string is stretched. So here we're given if 64 pounds of force stretches the spring a distance D of 8 inches, write an equation. So we're going to use this information to find K. So I'll substitute in. So 64 is equal to K times 8, which means that K is equal to 8, dividing both sides by 8. And then we can write our model. So our model is F is equal to 8 times D. That's the model. And then we're going to predict the amount of force that is needed to stretch the spring to 14 inches. So now we can use the model. So we're going to use the model. So this means that D is equal to 14, and we're going to find the amount of force. So F is equal to 8 times 14. So 8 times 14 is 80 plus 32, which is 112. And the units here are in pounds. Okay, let's flip to the next page. So another type of direct variation relates one variable to a power of another variable. So the last one was just linear. Now we're going to do a power. So for example, the formula for the area of a circle is A equals pi r squared. For this formula, pi is the constant of proportionality. This type of model uses power functions, which we learned about in section 3.2. Okay, so we can have direct variation as an nth power, and then these are the equivalent statements here that you need to be familiar with. So we can have y varies directly as the nth power, y is directly proportional to the nth power of x, or the equation that we're going to have is y equals k times x to the n for some constant k, where k is a constant of proportionality. Note, the model we just studied, y equals kx, is a special case where n is equal to 1. Okay, let's try a couple examples now when we have direct variation, but it's not a linear direct variation. So here's the example. I'll read it first. Neglecting air resistance, the distance s that an object falls varies directly, so this is our key, as the square of the duration t of the fall. Okay, so this is going to help us write our model. The next sentence is going to help us find the constant. An object falls a distance of 144 feet in 3 seconds. Okay, so let's write the model. So S, the distance an object falls, varies directly. So I'm going to put my constant K as the square of the duration of the fall, where the duration of the fall is given by the variable t. So K equals t squared. Now we need to use the given information. An object falls a distance of 144 feet in 3 seconds. This is going to help us find K. So let's substitute that in. So falls 144 feet. So 144 equals K times 3 squared. So K is equal to 144 divided by 9, and 144, let's see, this can be simplified, right? Because this is 12 times 12, so this is just 16. So K is equal to 16. How far will the object fall in 5 seconds? This is asking us to use the model. Okay, so now we have our model. Oh, I didn't write the whole model, so don't make that mistake. So S is equal to 16. Once I found K, we have to go back and put that back into our model. Now we're going to use the model. In this case, T is 5, so substitute this in. So S is going to be 16 times 5 squared. which is 16 times 25, and 16 times 25 is 400. So this is going to be 400, and the units here are feet. Okay, the next model that we're going to talk about is inverse variation. So we just did direct variation. Now we're going to talk about inverse variation. Okay, so the following statements are equivalent for inverse variation. Okay, just like we had for direct variation, we have different ways to represent inverse variation. So we can say y varies inversely as x, y is inversely proportional to x, and then our model is y equals k divided by x. Okay, and if x and r are related by an equation of the form y equals k over x to the n, then y varies inversely as the nth power of x, or is inversely proportional to the nth power of x. So we're combining the two ideas we have with direct variation for inverse variation at one time. Okay, let's flip to the next page of the notes. Okay, so now we are asked to determine if we have direct variation or inverse variation, okay, using the two models. So we've got y equals kx and y equals k over x. One is direct, one equals inverse. So you might want to pause the video, try these out on your own, and then check with the work that we're doing here. So in the first model, I have y divided by 2.6 equals x. I can rewrite this as y equals 2.6x. So this is an example of direct variation, right? We're just putting this into the form y equals kx. Okay. The next one, I have x times y equals 3. If I isolate y, I have y equals 3 over x. So this is inverse variation. The next example is y equals 5x plus 9. So in this case, it looks kind of like direct variation. Oh, I need the x there. It looks like direct variation, but I have this plus 9. So this is neither. This is a linear model, but not direct variation. It does not, the graph will not go through the origin. The next one, if I have y equals kx and k is negative, then I would get a line of this sort. This is the line here. So this is actually an example of direct variation, but k is negative. So this is direct variation. Okay. Now we've got a table of values. So we're going to see if I have direct variation. For direct variation, what are we looking for? In direct variation, I know that y over x is a constant. Okay, so if I look at my table, if I can divide y by x and I get a constant, it's direct variation. And if I have inverse variation, then y times x is a constant. Okay, so let's use these two ideas in order to determine what we have in the tables. Okay, so in letter D, in this example, if I look at y divided by x, the first one, 45 divided by 5 would be 9. 22.5 divided by 10 would be 2.25. So this is not direct. Let's check inverse. So 45 times 5. So I'm actually going to check x times y for each of these. So x times y here, 45 times 5 is 225. X times y, 10 times 22.5 is 225. 15 squared is 225. And 20 times 11.25 is 225. So this is inverse variation. Okay, and let's check So this stuff that I put in here, this is really just some notes as to how to work with it. Let's do the last one. So now we're going to look at is x times y a constant or is y divided by x a constant? So if you look at x times y, here we're getting 3 times 1 is 3, 6 times 2 is 12. So it's not inverse variation. And for direct variation, y divided by x in each one of these cases is 1/3. 1/3, which is the same as 2 over 6, which is the same as 3 over 9, which is the same thing as 4 over 12. So this is an example of direct variation. Next idea is we can talk about joint variation. So now we can combine the ideas that we had for direct and inverse variation with multiple variables. Okay, so we can have statements such as, let's go back. Joint variation occurs when a quantity varies directly with the product of two or more other quantities. Okay, so I can say z varies jointly as x and y. Z is jointly proportional to x and y, or the statement z equals k times x times y. These are all equivalent statements. And we can also have things with powers. So if x, y, and z are related by the equation of the form z equals k times x to the n times y to the m, then z varies jointly as the nth power of y and the mth power of, the nth power of x and the nth power of y. Let's try an example. So we're going to write the model and then use the model. So we're given that z varies jointly with x and y. So my model, my template is z is equal to k times x times y. And now we're given some information that we're going to use to find the constant. So this is the information we use to find that constant of proportionality. So z is equal to negative 84 when x is equal to negative 4 and y is equal to 3. So if we solve this, we're going to get k is equal to negative 84 divided by negative 12. So k is equal to 7. And then we're going to go out. We have to substitute this back in to get our model. So our model is z is equal to 7xy. That's our model. And then we're going to use our model to find z when x is 5 and y is 2. So using the model, z is equal to 7 times 5 times 2, which is 70. Okay, so using the model, we get z is equal to 70. Okay, going on to the last page. So on the last page, we're trying to translate words into an equation. And here we are combining joint variation and inverse variation, and we can have both of those in the same expression. So if m varies jointly with n, p, and q, we would have m is equal to, varies jointly means we have k times n times p times q. If r varies inversely, so that means r is equal to a constant over s. That means r equals k over x. X varies inversely with the cube of y, so x is equal to some constant divided by y cubed. Next one, f varies jointly with x and y and inversely with m. So we're combining joint and inverse in the same model. So we're going to have f is equal to jointly, so we're going to have k, and then in the numerator, x, y, and in the denominator, m, because that's the inverse part. And t varies directly, okay, with u. So we're going to have k times the letter u, and inversely with w. So w goes in the denominator. The rest of the notes are practice. The answers are on the last page. Thanks for working on these notes, and questions will be answered next time in class.